Assalamualaikum warahmatullahi taala wabarakatuh. EBCT3103 Construction Technology. My presentation is about Building Information Modeling (BIM) in Smart Built Environment (SBE). My name is Khairul Anwar bin Muhammad Yusuf, Applied Science, Bachelor of Science in Project and Facility Management with Honor (BPFM), semester May 2020. 1.0 Introduction on BIM and SBES. 1.1 Introduction on Building Information Modeling (BIM). As of today, Building Information Modeling (BIM) is a well-known model used as a resource throughout the construction process, from design, construction, management and operation, and finally, the demolition stage of a building. Another term used for BIM is ND modeling or virtual prototyping technology. American National BIM standard is defined. Building Information Modeling (BIM) is a digital representation of physical and functional characteristics of a facility. A BIM is a shared knowledge resource for information about a facility, forming a reliable basis for decisions during its life cycle, defined as existing from earliest conception to demolition. NBIMS 2010. Meanwhile, Azhar, Khalfan and Maksud 2009 cited that the Associated General Contractor of America (AGC) perceived BIM as Building Information Modeling is the development and use of a computer software model to simulate the construction and operation of a facility. The resulting model, a BIM model, is a data-rich, object-oriented, intelligent, and parametric digital representation of the facility, from which views and data appropriate to various user needs can be extracted and analyzed to generate information that can be used to make decisions and improve the process of delivering the facility. From the technology perspective, a BIM model is a project simulation consisting of the 3D models of the project component connected in a link with project planning, design, construction, or operation as shown in Figure 1 below. Figure 1 shows a visual representation of the BIM concept from Azhar ETL 2009. B standing for building, part of programming and design. For example, residential, commercial, healthcare, institutional, sports, and entertainment. I standing for information, a part of pre-construction and construction. Example, spatial, element, systems, quantities, schedule, and operation. And the last one, M standing for modeling, a part of operation and demolition. For example, site, architectural, structural, MEP systems, sustainability, and management. In BIM technology, the series of smart objects are defined. in terms of building elements and systems such as spec, walls, beam, and columns. A building information model carries all information of the building, including physical and functional characteristics as well as project life cycle. BIM can be viewed as a visual process where all team members and stakeholders can collaborate effectively in a single system of a facility or project. Team members can continuously monitor, refine, and adjust their tasks to project specification to ensure the model is accurate as possible. Integrated Project Delivery (IPD) is the latest concept to emerge within BIM. IPD brings together design professionals, owner and key construction management, fabrication suppliers, and product manufacturers to produce and optimize design into lifecycle management. Figure 2 shows how the BIM process takes place compared to the traditional process. Figure 2 shows traditional and BIM processes. Traditional process, concept and design document and drawing construction and operation. BIM process, relational database, design, document, and data. Active across sharing and data use to construction and operation. 1.1.2 Risks and barriers of implementing BIM. Risk of implementing BIM in a project can be categorized into, namely, technology-related risk and process-related risk, as tabulated in Figure 3 below. Figure 3 shows two categories of risk of BIM. First category, technology-related risk. A. Lack of BIM standard for model integration and management by multidisciplinary teams, which can create inconsistencies in the model. B. Interoperability issues, whereby the ability to exchange data between applications to facilitate automation and avoidance of data re-entry is lacking. C. Licensing issues. And second categories of risk of BIM, process-related risk. Lack of determination of ownership of the BIM data that need to be protected through copyright laws and other legal matters. And contractual issues of who controls the data entry into the model. This is bound to arise in the case of inaccuracies. The following are barriers of BIM implementation based on a study conducted by Koo and Taibat 2011, such as A. Learning curve and lack of skilled personnel. B. High cost. C. Reluctance of other stakeholders. D. Lack of collaborative work processes and modeling standards. E. Interoperability. F. Lack of legal and contractual agreements. 1.2 Introduction on Building Information Modeling for Smart Built Environment (SBES). Zhang, Sid, and Lai 2015. Relate smart built environment and built environment that embedded with smart objects such as sensors and actuators with computing and communication capabilities, making the environment sufficiently smart to interact intelligently with and support the human users in their day-to-day activities. In addition, smart building not only improve personal safety, comfort, and productivity, but also offer better support in terms of operation and maintenance of the building. The design and management of SBE generally focus on two aspects, service and sensing. The survey refers to that provided by SBE to support users in their daily lives. Vendor Meir, Jennings B. Barrett K. and Carol R. 2003 discuss the service life cycle and design principle of management framework of effectively managed autonomous and adaptive service in smart spaces. In proceedings of the IEE/IPSJ, a smart shadow system was proposed to provide home users with real-world services defined as services that affect the real world by changing the user's environmental factors, such, such as air conditioning and lighting, and to dynamically detect and resolve service conflict. 'On the other hand, some design approaches consider sensing as one essential component of SBE. Dong J.S., Feng Y., and Sun J. 2004 utilize a logic-based modeling language TCOZ, time communicating object Z, to describe constraints of the sensor imposed by its environmental condition or relation with other sensor and its sensing pattern, such as periodic or conditional sensing. The sensor-based model was applied to the design of smart spaces in detecting service chain and feature interaction in sensor-driven home network services (ECA) event, condition, action. Rules are introduced for describing home-based sensor-driven services, which can often cause a chain reaction. Example, one service may generate an outcome that automatically triggers another service. Therefore, a method is proposed to detect such service chain and the possible conflict among these services. 2.0 Discussion of BIM in SBES. Building Information Modeling (BIM) provides architectural 3D visualization and a standardized way to share and exchange building information. Recently, there has been an increasing interest in using BIM not only for design and construction, but also the post-construction management of the built facility. With the emergence of smart built environment (SBE) technology, which embed more space with smart objects to enhance the building efficiency, security, and comfort of its occupants, there is a need to understand and address the challenges BIM face in the design, construction, and management of future smart buildings. 2.1 Contribution of BIM in SBES development. In recent years, researchers have also explored how SBE design and post-construction management could benefit from harnessing BIM information and capabilities. In proceedings of the first ACM workshop on embedded sensing system for energy efficiency in buildings, An indoor wireless sensor network (WSN) is designed with BIM data that provide a detailed description of the building environment, which is required for accurate prediction of signal propagation and therefore link quality between sensor nodes in the building. In toward a ubiquitous smart space design framework, a three-dimensional smart space design framework was proposed in which space, example, furniture, walls, floor, etc., was viewed as one dimension along with technologies for ubiquitous computing and living, example, safety, health, and sustainability requirement as the other two dimensions. But et al. 2009 proposed an ontology-based spatial terminological inference approach to validate work in progress design of smart environments. The approach checks the design for compliance with the spatial and functional constraints of environment entities based on available architecture data in IFC format. Why not? Especially for smart built environment, it is also shown in application areas and data requirement for BIM enable facilities management that BIM can benefit post-construction facility management such as locating components, checking maintainability, and creating digital assets through its powerful visualization, analysis, and control capabilities. There are a number of existing work on integrating BIM with real-time information. For example, the Autodesk Research Group integrated BIM with sensor and meters to provide 3D visualization of building performance and lifecycle operation. The Virtual Real-Time Information System (VRIS) combines an ONUMA cloud-based BIM tool with a real-time sensor engine called the Virtual Real-Time Operating Center (VROC) to provide building management functions. However, when it comes to energy management, to the best of our knowledge, there are no existing BIM-based solutions in smart building environment with a smart grid. 2.2 Challenges in integrating SBES into BIM and built environment. As mentioned before, a variety of smart objects will be ubiquitously and transparently installed in SBE to perform action such as sensing and control. These smart objects may interact with each other and with the environment and the environment users. The communication can be carried by either wireless, example Zigbee 802.11 A/B/G/N or wired, example Ethernet Powerline Information Network. As general challenges in integrating SBES into BIM and built environment, a number of questions arise when considering the life cycle of a smart built environment. First, in how the smart objects are embedded in the environment. From the aspect of sensors, the physical location and the surrounding setting can significantly affect their ability to carry out specific tasks. Example, ambient light or occupancy sensing. From the aspect of the information network, whether a wireless sensor network WSN or wired Ethernet is deployed, it should be designed to offer the smart object an excellent level of communication. Second is how the smart object interact with the environment. The smart objects are situated in a specific surrounding to carry out their tasks and often require the input of space data, such as building floor plans. Furthermore, in carrying their tasks, the confluence of the action by different smart objects may involve affecting a common set of environment factors, the impact of which should be studied and understood within a spatial context. Last but not least, when conducting a building performance analysis, such as an energy efficiency analysis of the SBE, not only the information from sensor or meter is vital, but the building architecture or geometry data are also indispensable. Third is the maintenance of such smart objects in a building post-construction phase. In building management, it is common for facility managers to complain about their incomplete or inaccurate, not up-to-date documentation. To maintain a smart built environment that is more complicated than traditional structures, more building design and construction data will need to be documented and conveyed to the facility managers. In the event that the company that designed and constructed the building is no longer in business, building management can continue to function properly provided that the documented information is both comprehensive and reliable. 2.3 Conclusion: BIM in Smart Building Environment, where BIM hosts the collaborative architectural information and provides the semantic knowledge of the building. With the emergence of smart built environment technology, BIM should be further developed to be capable of seamlessly integrating smart objects in building design, verifying the SBE design and feeding smart objects with relevant build-related information. Design SBE with BIM is both advantageous and convenient. Firstly, designer of SBE can utilize the building knowledge of BIM for planning the layout of sensors, tags, actuators, and meters. The performance of smart objects can be verified against known constraints and their layout optimized for the best functional performance. Secondly, BIM also serves as a data repository for the physical information of smart objects. For maintenance and asset tracking in the building post-construction phase, the hardware information of smart objects can be recorded and their installation location can be documented and visualized in 3D. On the other hand, BIM provides a perfect ontology database for SPE. Smart objects may be designed and manufactured by different vendors. The data they provide may vary in structure and they may communicate using different protocols. Middleware is a popular approach to addressing such issues with heterogeneous smart objects. With the introduction of BIM, each smart object can be profiled through its information exchange interface. Because BIM is standard compliant, the middleware can extract data format of smart object and other building information for viewing as an ontology database. Sekian, terima kasih.